In this video, let's take a look at example number 3. Now, what's kind of interesting here about this example is that it's very different than a lot of the ones we've seen before. In the previous examples, we were always kind of told what region we were going to be integrating over, what function we were going to be integrating. But here, we're just kind of given this iterated integral and asked to evaluate it. Now, at first glance, maybe this would seem like, okay, well, this is easy. I don't have a lot of setup to do. But what I'll notice here is that I have to first start by integrating with respect to y. But if I look at what's here in the integrand, sine of y squared, and I start to think like, well, what would the antiderivative of a sine of y squared be? That's actually super difficult. In fact, that's actually an impossible function to find an antiderivative for using what we would call elementary functions, or what you would commonly more think of as just all the functions that you already know and love. So the only way to maybe try to do an antiderivative of something like this would be with like a Taylor series or something horrible and nasty like that. So what is really kind of tricky here is that the way that this iterated integral is set up makes it way too difficult to calculate. So what I'm going to go ahead and do here instead is to note, or to try to kind of figure out from this what question would have been posed that would have led to this integral. Like clearly I'm finding the volume under the surface z equals y squared, but I need to figure out over what region. So let me go ahead and kind of write down what it is that we're thinking of like this. So I'll say we see that this integral is very difficult to calculate in its current form. Again, that's because of that sine of y squared not having an easy antiderivative. So what I'm going to attempt to do is to try to figure out, again, what is the region that we are integrating over. So I'll say we see that we are integrating z equals the sine of y squared over some region d. So I'm going to start here by just trying to figure out how d is actually being defined based on the way that my bounds are set up. So here I can quickly note that d is going to be some region in the xy plane, collection of xy points, and I can see here that x to 1, well, those are bounds on my first integral, which means these are bounds on this variable of y. So I note here that x or y is bounded between x and 1, but then I can also see from the outer integral that x is bounded, that x integral is bounded between 0 and 1. So I can see here that d has been communicated to me, but I'm interested in what d would actually look like. So I'll say we draw a picture of d. Okay, so let's see here. I know that x is going to go from 0 to 1, but I need to think about what this means. My y values are bounded on the low side by x. That is implying here that there is going to be a line of y equals x in my picture. So if I was to go ahead and draw this, here's like my line, y equals x. And I can see that my region has this line as its lower y bound. So if I think about this region with a top and a bottom, the bottom of my region is bounded by x. The top of the region would be bounded by y coordinate 1. So I can start to see here that then this region appears to kind of meet all the appropriate criteria. It's bounded on the top by y value 1, on the bottom by y equals x, and x across this region goes from 0 over to 1. So if this here is my region, I can go ahead and try to find a way to re-express this. Again, I thought about this as a region right now that had a clear top and bottom, but what if I thought about this region with a left and a right bound? So I'll say that we redefine D as a collection of xy points out in the xy plane, But now notice I can think about bounds on x. So again, like we talked about before, if I imagine I have myself inside of this region, if I walk all the way to the left, regardless of how up high my point is, this side over here of x equals 0 is always going to be my bound. And if I was to slide all the way to the right, no matter where I was inside of this region, I always hit this line again. But now that's x equals y. So I kind of think about that line solved for x. So I have this, my left is 0, my right is the line y equals x, and then of course I can state what my overall bounds are for y, which is lowest y in the region is 0, highest y in the region is 1. So now this allows me to think about rewriting my integral. So I can say here that the integral that I used to have of sine y squared dy dx, I can now think about as I can re-express this integral now in the form of dx dy, where x is bounded from 0 to y, and y is bounded from 0 to 1. Now you might be thinking, Kyle, how does this really make anything easier? Because I still have to integrate sine of y squared. But actually, this is a lot easier now because I have to start by integrating with respect to x. So actually watch how easy this now becomes. When I'm integrating with respect to x, I treat sine of y squared all as a constant. So the antiderivative of that is just going to be the sine of y squared times x. And then I evaluate that from 0 to 1. Okay, well, if I simplify that up, that's going to look like the sine of y squared times y minus the sine of y squared times a 0, which I just won't bother to write right now. And you might still be thinking, Kyle, how did this make anything easier? Don't you still have to integrate a sine of y squared? Kind of, but now notice there's this extra y here. And I can quickly go ahead and see that if I was to say, like, do a u sub here, I could say let u be equal to y squared, then du is clearly equal to 2y dy, which is great because I almost have 2y dy here. I'll simply just take 1/2 multiplied to both sides, and now I can easily see y dy can get replaced with a 1/2 du, and y squared can be replaced by u. The only other thing, remember, that I always have to do when I'm doing a u sub is I also need to change over the bounds of the integral, and I use my starting substitution value to do that. So I would say here that if I go to u formula and I plug in 0, well, this tells me that my new lower bound is 0, and my upper bound here, which used to be 1, I have to square that. Okay, it's actually also 1. So even though I'm doing a u sub here, I can easily tell that this is going to still be an integral from 0 to 1. I'm going to have a sine of u, and I'm just going to have this extra 1/2 multiplied out in front and my du. Of course, my antiderivative of this is just going to be a negative cosine of u, and I just have to evaluate this from 0 to 1. All right, so let's see, when I plug in the 1, I'm going to get negative 1/2 cosine of 1. I don't really know what the cosine of 1 is. That's not a nice unit circle value, so I'll leave that. And then I have minus negative 1/2, so that turns to a plus, and the cosine of 0. The cosine of 0, I do know that does turn into a value of 1. So if I was to rewrite this here, I could write this as like 1/2 minus the other half cosine of 1. Notice here again, I just did reorder this so I could, instead of having a negative, I could think about doing a subtraction. Okay, so this is a really important thing to note. If I'm ever given a double integral, or sorry, an iterated integral here, and I'm asked to evaluate it, but I can't figure out how to do it in one direction, I can always attempt to determine what the value, or what the region D is and how it's defined, find a way to flip that around. If it was used to be defined with a top and a bottom function, think about defining it with a left and a right, or vice versa. And maybe by doing that, I can turn the integral into an easier state that then I can start to deal with.